All right, so now you don't even need to turn, but I don't see myself.
You can see yourself here.
Yeah. Great. So then we try a new setup. So let's start.
Feels way more complicated than it should be.
Okay, so today we will be talking about variational approach, and this is just a very quick reminder. Hopefully you all heard about that approach in general. It's an undergraduate, almost like material, and in any quantum course. And just a reminder there to get some initial introduction to the variational quantum Eigensolver, which is the method that we're going to be considering for today. Hopefully we'll get that today. And also there are a few aspects of BQE that we will be talking today and hopefully for tomorrow and Friday maybe. Okay, so let's start. Great. So the motivation for variational approach is very straightforward. You'll probably know it. Most of the interesting quantum problems, they don't have exact solution like particle in the box. So then we could build the solution using this variational theorem, and you'll see the variational theorem once or several times. And the idea is that if we have a Hamiltonian or any operator really for which we would like to find the lowest eigenstate, right? So we could build approximation to that eigenstate using the fact that you cannot go below the lowest eigenenergy. And that's what variational theorem sort of shows, right? So we have a operator H here with a spectrum that is bounded from below, right? So there is a bottom, and then essentially whatever state you provide, this expectation value will always be above the ground state, right? And that's great because then you could simply minimize the parameters. So the state is parameterized somehow with maybe one or maybe multiple parameters theta, and then minimizing with respect to this parameters theta, you could get as close as the parametric space will allow you to the actual ground state. So this is straightforward. Turns out that you could technically use the same idea to kind of approach the other states, not necessarily ground state, because you could just look for the extremum of this functional that we have, and not necessarily get to the minimum, but to the saddle point, which would correspond to some other state rather than the lowest state. We cannot pass the ground state, and the important conditions is that the boundness of the operator. Another important condition is that the operator that we're dealing with should be a Hermitian, right? So this is something that is important in proving the variational theorem, because without hermiticity, the operator still can have a spectrum that is nice and bounded, but the eigenstates of that operator, it's not Hermitian, could be, we could have multiple eigenstates, left and right sets essentially, and things in the variational theorem not quite all work out. That sometimes is important because if you try to change your Hamiltonian to leave the spectrum, let's say with some similarity transformation, or to modify the Hamiltonian so that maybe the eigenstates will be simpler, but the spectrum will be the same. And that similarity transformation if T is a general operator, not necessarily operator that is let's say anti-Hermitian, right? So in this case, then this operator transformed H is not Hermitian or anti-Hermitian. It's just general operator, and then you won't be able to apply the variational principle for it anymore, unfortunately. Now, if we're working with a T that is let's say anti-Hermitian, in that case, the exponential function of T is unitary, and then transformation of unitary leaves the hermiticity. It's easy to check. And in such transformations, the Hamiltonian stays unitary, and you use variational principle again. But unfortunately, the general similarity transformation is taking us out of the domain of operators where you can use variation principle.
The closeness of solution, you just mean the energy, right? You
Yeah.
cannot measure the closeness of solution.
Okay, so that's an interesting aspect. It's like one can ask the question how close we are to the, let's say, if we have a phi, right, and we know that there are eigen states, right, for the Hamiltonian. And the question could be, okay, can we estimate what's the overlap between, say we are trying to get the ground state, right? And this is a true ground state. So what is the overlap here? That's the closeness, right? And so it turns out that there are ways to estimate, like one idea would be you want, let's say, lower bound for this quantity, meaning that you want to have an expression that that this overlap, let's say, is larger than the expression that some function of phi theta and let's say maybe energies of the Hamiltonian, right? So, and this is always low. Essentially, this is always lower or equal than the true overlap. Right, so there are ways to construct such functions. One of the easiest, it's relatively easy to show from the a few lines of algebra, is that if you have, let's say, expectation value for this phi theta, right, H phi theta, and use them, this is what will be important is E0 and E1, right? And let's say this quantity, the expectation value, is somewhere in that gap. So then it's always going to be larger than this. And let's say it could be higher than E1. But let's say if we're in a good situation where it is in between, then there is a way that the expression will be, see the following. So it's I believe it's a E1 minus this expectation value divided by E1 minus E0. Okay. So this simply means that, okay, so if we get to E0 with this quantity, we will get 1. Right. So this energy that we're getting, if it's the same as E0, then we're getting this ratio to be 1. That's good. That's how it should be. Now, if this quantity is larger than E1, what we're getting is a negative expression in numerator, right? Because we're subtracting E1 from E1 something that is larger than 1. All right, and that makes it negative. So that is also sort of making sense, because if your function is really far away from the being a function of the ground state, then you get in the lower bound for the true overlap, which is always this thing is always larger or equal than 0 and less or equal than 1, right? So this estimate, if it's negative, is just useless, right? And so it's only useful if we are in between the E0 and 1.
And E1 is just first excited state?
First excited state, right? So as long as you can get your expectation value in that gap, right? So then the overlap, like we could guarantee with using again a few lines of algebra that this is called, this has a name as I learned, but you could derive it yourself. So it's called Eckert bound. And it simply could be derived if you expand this again in terms of eigen energies and overlaps, of course. And then you substitute all the energies in that expansion by E1, right? So of course, if you have ordered sequence of energies, like E0 is the smallest. Okay, it's a few lines of algebra. Let's right. So if you have this sort of sequence of energies in the Hamiltonian, then what we can do, we could analyze. Okay, we have phi theta h phi theta, right? This is equal to sum over all these energies, pk and pk, where pk is these are overlaps. pKs are theta through eigenstate. You could a square, so square. So this is the general expression, and then that expression, let's say, for short notation, it's E bar, right? So this E bar then will always be smaller or equal if in that expression, what I will do, I will take the E0 term, P0, that's a ground state, an overlap to the ground state. And then I will take all the other states and substitute them by E1. All other states are larger than E1, right? So then I will make this expression only smaller because the P1, P2, P3, they're all positive, right? So therefore, if I reduce the prefactor in front of them, that will only make the expression smaller. So then I will have here sum over pk from 1 to any large, like whatever number of eigen values I have, could be infinity, could be finite. So then this is the substitution, but also this substitution allows me to, using resolution of identity, to say that this is 1 minus P0, right? Because some of these overlaps will be just simply 1, right? Because it's a expansion of the normalized function in a problem. And so that allows me to write down now the expression, which is E bar, always less or equal than E0 minus 1, P0, and then I will have also plus E1 expression. I will move E1 here to come with minus, and I could divide by this expression, and I need to change the sign of the this inequality because division, like this quantity is negative, okay, because E0 is lower than it. So what I will get is that the P0 is less or equal. I change this to yeah, E0 is equal to less than equal than E bar minus E1 divided by E0 E1 and then I could just simply change for convenience E1 to the bar, and then E1 minus E0. Right, so this is the expression I wrote here, right? So this is one of the simplest ways to estimate how close we are in terms of the overlap. But yeah, it still requires knowledge of E1 and E0, and or at least guarantee that you are in the gap. If you are not in the gap, then yeah, it's just useless, right? So one would need to use other quantities in general. This is an interesting problem you're kind of pointing out that, and it will be interesting for other algorithms that we will discuss. For one of the kind of important algorithms in quantum computing, it's important. It's very crucial to start with some state that has a good overlap with the ground state where you want to essentially converge the algorithm or investigate with using that algorithm. And there are currently somewhat debates in the community whether it's easy for all the systems to prepare such kind of trial function with a good overlap rather than good energy. Okay, and so this consideration at least tells me that if the system has, like from experiment, let's say we know that the gap is significant, then it's not that hard to get a good overlap. An example could be if we are studying some organic life emitting diet, then the difference between it's usually invisible range. And so that means at least one, let's say EV difference in energy between the E0 and E1. And usually what we want is to get the energies with accuracy that is millihartry. And that is 0 less than 0.1 eV. So essentially, as long as you are in that gap somewhere, at least somewhere in the middle, like 0.5 eV, then you will have a good overlap, right? Even without having a good energy. Okay. But there are some situations, of course, where the gap is small, then it may become difficult to get a ground state with like trial state with a good overlap. All right. So these are some books where you could read more on the various aspects of variational principle. And here I just want to say that, well, in classical computing, we use variational principle, let's say, starting with a very simple Hartree-Fock approximation. One can think of it as optimizing the orbitals in a Slater determinant in order to minimize energy, but the kind of a wave function is approximated by a single Slater determinant ansatz, right? So we know the solution for hydrogen molecule is sigma sigma star in the minimal basis molecular orbitals, right? But I guess one can think in terms of second quantization. The expression for Hartree-Fock could be formulated using the unitary rotation, because when we optimize orbitals, we could think of it as a unitary rotation within a single orbital space. Right? We probably will get to that at some point. Just a remark. Here, the Slater determinant we obtain is just the one configuration out of many possible, or 4 possible, or if you want to preserve the right number of electrons and spin. And then some others would need to be included if we want to go and well, make things more accurate. Single doubles. So this is what leads us to the usual configuration interaction expansion. And this is what is done also on a classical computer as a way to, again, use a variational principle. We first optimize maybe orbitals and then go and optimize the coefficients in front of all the Slater determinants that one can obtain. Right, and in this small case, they all can be written explicitly. Okay. All right, so now if we want to use variational principle in the qubit space with a quantum computer, generally the idea is the same, but everything is put not maybe as a linear ansatz, but as a unitary ansatz of some sort, right? So that again, we will be looking at essentially unitaries that live in a Lie group, and we will look through this Lie group of unitary rotations and trying to figure out which unitary transformation to take so that we could start with some simple state and it will rotate into state that corresponds to the eigenstate, right? So that's the basic idea. We have a group structure, so the products of unitary is unitary again. And what usually happens is we just keep adding the unitaries until we converge to lowest energy possible within the sort of number of unitaries that we can fit on the quantum circuit, right? So every unitary has a certain expression in terms of the things that quantum computer can do. And these are somewhat technical aspects that probably not going to go too much into. It's more like on the compiler level is that there are certain simplicity of unitaries that would, or like there's certain blocks that if you give a compiler, then it will spile it into the actual gates that the quantum computer can do, right? And usually my basic I guess understanding of this process is that as long as you can formulate your unitary as something like Pauli product exponentiated, so that is already enough to put this unitary on the quantum computer, right? So technically, this there is an easy way to show that any n qubit Pauli then can be written as a product of just a single qubit Paulis and two qubit Paulis, let's say 1 or I1, and then product of say P2. So and then they can be put on the quantum computer. So we don't really. Well, some people worry indeed how to, if you provide them complicated unitary, how to do this in the most efficient way. But it's interesting problem if you don't know how to decompose unitary into the product of the such elementary unitaries. But once you have that, it's already more or less the problem that is solved at the compiler level. So most of the softwares that are available there with IBM or other vendors, they will do it for you if you can formulate your unitary in terms of this Pauli call it exponential functions. Okay. All right, so you could now think, okay, how does the wave function look like in this kind of new form compared to, let's say, what we saw for the normal classical theory. And as in the normal classical theory, I want to make an analogy here. And in the normal classical theory, we did the orbital rotations, and then we did the configuration interaction. So sort of the idea was that there is a mean field level, a single particle, like when we rotated orbitals, it's a single particle level. And then when we put like more configurations, that's a so-called electron correlation level, right? So with qubits, it could be done the same way. One can technically introduce a mean field that rotates individual qubits, and we already seen these generators here. These generators that rotate in individual qubits, they could be written as a single SU2 rotations for the each qubit, and then since all qubits commute, then you just take the product. The order doesn't really matter because they commute. And in the exponent, we have one angle here, theta, and then n is the axis around which we do the rotation. Okay. So that you could think of as a qubit mean field. And because we now know that the orientation of qubits means something in terms of like original orbital picture that we started with, one can think of this as a like analog of Hartree-Fock. But it turns out that because of the way things are mapped in the case of like Jordan-Wigner or any other fermion qubit mapping, it's non-linear mapping. And therefore, it turns out that in some cases, this qubit mean field theory produces results different than Hartree-Fock. And what I mean by different is that you could imagine just taking the same Hamiltonian, right? Starting with the fermionic Hamiltonian for any molecule like H2, for example, we have electronic Hamiltonian in the second quantization, A in dagger, right? And then you could either go and do Hartree-Fock theory, or you could do Jordan-Wigner transformation or any other transformation, get the qubit Hamiltonian. As I was saying before, if you do exact treatment of the, like if you obtain exact spectrum of electronic Hamiltonian or exact spectrum of the qubit Hamiltonian, they will be the same. But if you apply now approximate way of getting the spectrum, which is the mean field theory, Hartree-Fock, the case of fermionic space, or this qubit mean field theory, rotating individual orbitals, then the results could be technically different because you are using approximate treatments, and these approximate treatments, they use different degrees of freedom. Because in the Hartree-Fock, we were rotating orbitals. In this qubit mean field, we're rotating the qubits, and they don't go like they don't essentially correspond to each other directly, right? So the details, I don't want to go too much into the details of this process, but details in that paper, which I will put as a reading material. But the simple explanation is that this qubit rotations, what they can do, they can break symmetries like even number of electrons, because if they flip the qubit from being up to being down, then that just changed the number of electrons in the system. While the Hartree-Fock rotations, they rotate orbitals, but they don't really change the number of electrons, because all the Hartree-Fock rotations, they technically the exponential functions of the following anti-Hermitian operators, theta, some sort. Here we have a Q dagger B, right? So this is our generators, Q, products, E larger than Q. So all this is Hartree-Fock rotations. So you can see the number of daggers and non-daggers is the same. So therefore, Hartree-Fock rotations, they will never change the number of electrons. If the system started with a certain number, we'll end up with that. But mean field rotations could do that. And also some other symmetries could be broken. Now, the next step is correlation, including some correlation. And here we, in the quantum computing language, could think of the correlation as an entanglement, because as we discussed, if the wave function cannot be represented as a single product, that's what is called entanglement in the quantum information language. And then this is like the spooky action on the distance as like this EPR experiment where if we measure one qubit, the other qubit will essentially react accordingly. And this is what makes the function complex, because now every coefficient in front of the H product could be different, right? And it allows us to essentially encode more stuff. Now, in order to introduce entanglement, on top of the mean field rotations, on top of the single qubit rotations, we now need to put multi-qubit rotations, and all of them could be parameterized by just exponentiation of the Pauli products, right? So the only downside of this picture is that the number of these Pauli products that you potentially can put is 4 to the n, where n is the number of qubits, so exponentially many. A little bit pause and reflect here. It's really, if we would need to use all 4 to the n Pauli products in order to describe our function, we are sort of in trouble, because even on a quantum computer, then the number of operations you would need is exponentially many, right? And that is not a good news, because we know that well, from technological point of view, that quantum computers are not faster in doing operations; they just do different operations, right? And so the hope, it's still hope because it cannot be proven exactly, that for chemical systems you could get away with the polynomial number of generators rather than exponential. But for representing the true powerful, or I guess the true truly any unitary in that space, you need the exponential many generators. Okay.
So is that the same argument as for clusters that we also have to find?
That's right. Yeah. So that's a good analogy for classical. I guess for classical computations, it's the same idea. The only difference is that there is a hope that well, that hope is based on certain kind of certain properties. Like, but the main I guess idea still is that we could, with building some heuristical method, we could reach needed chemical accuracy faster using quantum computer, right? Using different operations. So that's the hope. And well, let's see. But from the quantum, I guess not quantum even, but the computer science point of view, computer scientists, they like to consider the worst case scenario. And from that point of view, there are, of course, well, it was proven that there are two electron systems. You could make, if you allow yourself to do any Hamiltonians in fermionic systems, then you could get the ones that will be somewhat hopeless, and you will need indeed exponentially many transformations in order to get the well, solutions with a high accuracy. So it's just that we believe that nature is not against us; it's just indifferent to our attempts, in a sense, right? So it's, and the worst case scenario is good to know, but may not be the case. All right, so going beyond ground state, essentially, this is another aspect that some considerations already been made, because one could want to go beyond the excited state. As we were discussing, sometimes we need multiple surfaces in chemistry to describe the things. Again, to predict the spectroscopic observations. Sometimes it's excitation of electronic states, right? So how can we use the variational principle in this situation? We just need to change the functional, because usually if we stick with the same kind of functional, where just expectation value of the Hamiltonian, algorithm will essentially will try to get to the lowest state, right? And in order to avoid that, one can put some constraints using, say, symmetries. So symmetries are very useful because we know the Hamiltonian commutes with the number of electron spin and the electron spin operators, at least. Maybe some point group symmetries could be used. And since these all operators commute the Hamiltonian, they share eigenstates, and therefore you could add to the functional, to just expectation value, you could add that your some penalty term that corresponds to effectively having the expectation value of the symmetry operator being different than something that you already obtained. Let's say if you know that your ground state was a singlet state, S square the state of 0, right? Then you may wanna, if you wanna go for the triplet state, then we know it's like S plus 1 S, where S is 1 for the triplet. And so this is 2 then. And that expectation value could be used in that form, where instead of well, there's a penalty, you could put f by s squared phi minus, and you want to avoid s being 0, so you want to avoid collapsing to a singlet. So minus 0, it's really yeah. So sorry, it's what you want to avoid, yes, collapsing to the singlet, but you want to make a penalty, so therefore it will be 0 if you put the right essentially the eigenvalue for the symmetry that you want to achieve. All right, so minus 2, that would be the penalty term that you add, and of course, if that's a singlet state, then this part will be 0, but the 2 will be squared, and will add to the energy. So it will be, the energy will be higher. Of course, again, depends on what this lambda factor that you could use, right? So, but if lambda is large enough, so your system will try to get the phi state, which has this expectation value close to 2, so that the penalty will be close to 0. That's the idea of the penalty for this, using symmetries. Another approach is you could, if you found already the ground state by 0, then you could add the penalty term for having essentially non-zero or high overlap with the line 0. So you want technically overlap to be 0. So then there will be no penalty. And we know that the excited state will have overlap with the ground state 0, because they're all eigenstates of the Hermitian operator, so they are orthogonal to each other. But this technique potentially allows you to obtain the ground state and first excited, second excited, and so on. You keep adding the penalties with the overlaps. The only problem is that at every time you find only approximate functions, so it may not be like essentially you may end up with less and less accurate representations.
And this is because of numerical?
Yes, it is numerical, because every time you obtain only approximate ground state and first excited state. Right. So then there are some other techniques like equation of motion. It's very similar to the, I guess, property techniques that you guys use for the quantum computing work, right? And yet another way to kind of go for the excited states, which is a little bit more expensive, is, but nevertheless, it's always good to remember that if someone gives you a state, you could always say whether a state is an eigenstate or not for the Hamiltonian. For that, you need just to calculate variance, right? So variance is always going to tell you that you are in an eigenstate situation, because the variance then will be 0. But why is it more expensive? Is because the variance is requiring h squared, so applying h twice at least, and every time you apply h, it's the effort to do that. Or in a quantum computer, in terms of BQE, let's say, we'll see that h squared just will require more measurements because it's a bigger operator than h. Okay, but conceptually it's possible. Another kind of, I guess, similar technique with the h squared would be taking h, subtracting some value that you principle think where your state of interest is, and squaring. So that operator has essentially the state that is close to the tilde, again, ground state, right? And the other states will be excited states. So if one can do this sort of consideration, but that again requires you to deal with h squared and h. Okay.
So the orthogonality is, for instance, maximum overlap method
Mhm.
of delta CF. Is that the
It's
condition there?
yeah, I guess it could be related to the delta SCF, because in delta SCF people trying to find using the SCF the state with them. But then in delta SCF they try to find the SCF solution with the
problem.
I
but
said
the
like in
determinants-
the MOM method, this maximum overlap method that
ah
is used also in delta CF, but in
okay.
general, so.
Okay,
The
yeah.
MOM is just about how you create your alpha occupations, right? If you want to keep the same orbitals.
Yeah,
in
but
the previous
with the
iteration.
purpose of getting a solution which is not the ground state solution. Right, you fix the occupation of some orbitals and then you minimize retaining that occupation through some maximum overlap of the method. So the idea is you find a non-alpha solution of the variational procedure.
Mhm.
I guess
In-
it folds
But
probably
delta
with the,
SCF, does it re-optimize orbitals?
Yes,
It does, right?
Yeah.
Okay.
and that's why you need to keep the overlaps as close as possible to be able to follow each operation.
And yeah, then when the orbitals re-optimize, I'm not sure what's happening with the orthogonality, because I think that it's yeah, the method that sometimes obtains the just different later determinants for like approximation for the ground and excited state, but because they are later determinants with some different orbitals, they may not necessarily be orthogonal to each other.
Yeah.
Right.
I think you just orthogonalize in the end.
yeah, probably. I don't know.
Because it's after all.
Okay, so
right,
this orthogonality is not the same.
not
then.
the same.
Okay,
Yes,
okay.
because this orthogonality is sounds very simple. You could think of it as a we have the same orbitals. In that sense, we know that the higher states they will be orthogonal to the ground state, right? And if we find the ground state, in order to avoid the collapsing to the ground state, we are putting this extra penalty, because if phi becomes phi 0, this penalty term will generate plus lambda, right? And that's kind of a bad for the minimizing f. All right, so just to summarize this little review, variational approach is one of the most straightforward approximate techniques. Yeah, gets you numerically accurate solution if you have enough parameters. Then you don't need to forget that it's only for Hermitian bounded operators it's applicable. Getting excited states requires some extra work with penalties, constraints, or maybe initial guess and then making sure that you don't collapse to the ground state. Fermionic and qubit spaces, variational techniques somewhat could be similar, but if you do the variations in a qubit space, there's some symmetries could be broken, and that something that we'll see more in the result section. And then I guess the main challenge for the variational approach is to find the wave function form that has not too many parameters, right? Otherwise, it becomes too difficult to do the optimization. And ideally, you would want to keep it a linear optimization. That's why everybody liked the configuration interaction, linear algebra problem, right? So that there are efficient techniques, but once we go nonlinear, then things become more difficult to really ensure that you are in a global minimum or local minimum support. Okay. All right, so now we are well equipped to talk about variational quantum Eigensolver, which is the first quantum algorithm, really. And historically, it wasn't the first algorithm. First was the quantum phase estimation, which we'll discuss later. But the thing which motivated to create something like variational quantum Eigensolver was that this quantum phase estimation algorithm, it required initial state to have a good overlap with the true ground state, and somehow one needs to prepare that ground state estimate, right? Also, there was a technical issue that the computers back then and computers even now, they won't be able to just put all the transformations that need for quantum phase estimation because the error accumulate. So it's too many gates, right? And people decided, okay, why don't we solve both of these problems in the same way or with the same method, right? So just use energy and its minimization to get a good initial guess for the quantum phase estimation. And that unitary may not require as many transformations as the one that is quantum phase estimation. And then that was the initial motivation, but then people start abusing that in the sense that they decided, okay, why don't we just try to get energy instead of preparing the good state for the more sophisticated algorithm? We just, well, we'll do everything within the VP, right? And we'll go after energy, not really after preparing the good guess. And so that's how I guess it all started. And now it's even, yeah, these days, big, I guess, enterprise of creating various ansatzes for the wave function unitary circuits. And this is the original paper. There are more, of course, reviews, and there are more even after the ones that I put there. So it's a very simple algorithm, as you will see in a second. You probably already know, and that's why chemists really loved it. So you don't need to educate yourself too much. You could just start doing it. And yeah, I guess the developer and current colleague of mine at the University of Toronto, Alana Spraguzik. So the idea was that we use hybrid in a hybrid fashion quantum and classical computer, because just quantum computer itself is not powerful enough. So the purpose of a quantum computer is to prepare complicated wave function and then measure expectation value of the Hamiltonian of that wave function, right? So the way we prepare wave function is some unitary transformations applied to some simple state, right? To start with. And then there will be measurement at the end. And after measuring, we get an expectation value of the Hamiltonian with, and we know that there are some parameters we use to prepare the initial state or the trial state. And then we pass that information to a classical computer that suggests a new maybe guess for the parameters. And minimization is done either using gradients of energy or without using the energy of gradients with respect to parameters. But essentially, it's already a technical matter. But the loop is that the classical computer will suggest the different maybe unitaries with extra parameters, and then it just goes back and forth between quantum computer and classical, and the feedback loop, which eventually should get us lower energy, and that should be our approximation to the ground state, or maybe excited states if we modify the our operator to be rather than expectation value of Hamiltonian, but something more sophisticated. Okay, so that's a very simple idea. Now, interestingly, this idea really doesn't put any information directly to the about the Hamiltonian to the quantum computer, as opposed to say other like analogous techniques of quantum computing, where you really try to prepare your qubits so that they feel the Hamiltonian that essentially is equivalent to the Hamiltonian that you're interested in. Here we just measure the Hamiltonian at the end, and that's all.
So it means that you're skipping, say, Davidson iterations on a classical computer?
That's right, yes. So we don't really have anywhere in the quantum computer sort of where state meets the Hamiltonian technically. One can just, we will talk about the measurements more. It's an interesting problem, but really what we're going to be measuring is not, well, some parts of the Hamiltonian, but there is effectively some abstract operators that are universal in the sense, like the Z operators. And the Hamiltonian is sort of not exactly introduced as a part of the circuit as we do in more complicated algorithms. Okay. All right. So the two main challenges with this framework, even though it's a very simple one, is that it doesn't really give any maybe guiding principle besides energy to find the unitary transformation, and we know the unitary lives in a large space, right? So we actually know now that the Hamiltonian and its eigenstates, they live in the like a Fock space initially. Now it's a Hilbert space, which is the size of the Fock space. So it's a big space. And finding the unitary that will rotate something simple to something that is an eigenstate of that Hamiltonian is not trivial task. And it turns out another news here is that it's not like you could tell the quantum computer to measure any operator and it will do it for you. That is not working like that. The measurement of the entire Hamiltonian is a very challenging, and usually it's partitioned to some parts from which you then understand what's the expectation value of the Hamiltonian is. And it could be quite a laborious enterprise to get all the measurements, so it's not done in just a single step. Okay. Those are the two main challenges, and essentially the rest of the probably this week discussions will be about how do we address these two issues. But I guess it's close to 3:30. We should do a break, right? Okay. So let's do a 5-minute break.
Starting to understand what this quantum computing is about. So it's not like that you're really solving the same program on some infrastructure, but you just have to completely different algorithm and map the wave function.
Yeah, that isn't particularly the case of I guess eigenvalue problem where you're trying to construct an eigenstate of the operator. But there are other problems like let's say breaking the RSA key encryption, right? So there it's also right, Shor's algorithm. It's also could be related to finding the eigenvalues of some Hamiltonians, but in general, like the way I like to think about essentially quantum algorithm is that you have some sort of input information encoded in the state, and then you can somehow have a quantum algorithm which is like just a sequence of unitaries, and then maybe measurement at the end, or maybe it could be kind of the sequence of unitary transformations and measurements. That's possible too, and eventually you read out the answer after doing this unitaries and measurements, right? So the whole art of creating algorithms is that how they go from here to here by putting the unitaries and measurements in different in some of these cases, I guess in some cases we know what unitary and measurements we need to do. So the algorithm, like the quantum phase estimation, is already, or Shor's algorithm is already known. But yeah, I guess in the case of Shor's, you even know how to decompose this one unitary into the sequence of steps. It's just the number of steps is large for the current quantum computers. So there's
Would it be possible to have the slides uploaded before the lecture?
sure.
Then it's easier to make notes on them than when
Okay. Okay. All right, I'll do that. not always sure how far do we go, and projections, right?
Alternativet er bare sidst folk skal læse kursen. Det vil jeg ikke anbefale. Nej, det er meget skrevet, men jeg synes, det er ja, faktisk.
I'm a bit challenged whether it will stay at the end. I hope.
Are you saving in the cloud?
Yeah, but I never tried it before, and I'm not sure.
Trust the cloud.
Det er meget. Det kunne være på nogle punkter kunne det være smart.
Also had reservations.
Bare for at have det. Men der er nogle hvor det også og den bliver opdateret, så skal vi ikke få en reset ting ind i settings, og den skal også skal ting i selve driver, og så kan man jo ikke.
But I'm keeping a backup recording on this one, so the worst case scenario today doesn't work. This one, and this one.
Selvom det tror jeg så overvejer jeg bagefter, om jeg ikke på et eller andet tidspunkt må vi tjekke. Det er så ting, der er sådan som det tager.
These 2 points, actually, this is irrespective of anything related to noise, right?
Yeah, that's right.
So this is just the theoretical challenges, and then there's all the problem of actually of the real device, right?
Right. Well, sort of, one can say that, yeah, if the quality is not of the quality is not of the certain over the certain bar or some threshold, you won't be able to do anything. Generate the noise and end of the story. But, that's why it's,
it's the whole thing is feeding a lot of people, I would say. I mean, creating jobs and so on, but
Right.
but usefulness of the outcome is very questionable.
right. Especially the developments in the near term, it's like I at some point almost like stop doing anything along those lines, because simply if the error correction will happen, then it has future, and then but then the question is why to develop this algorithms that well, maybe will have fewer 2-qubit gates, which is important when you don't have error correction, but after the error correction it doesn't seem so important anymore, right? So yet there is a big army of people who are keep developing, like trying to make things fit to the devices, some molecular problems, and it's just all either going to be superseded by the error corrected techniques or will die. Like there is no future without error correction.
And if the error correction scales exponentially, then we are back to the origin,
Well,
right?
the error okay, so the error correction will scale, I guess, dependent on the quality of the qubits, right? So after certain, if you have a certain quality of the qubits, error correction is not that bad. It's just a constant 3-factor, which is big, but still constant. People in the area, like experts in this field, are still pursuing that, right? So putting the billions of dollars. Like Google and IBM, right? So developers.
But if you have to use, like, I don't know, hundreds and hundreds of GPUs to correct. Right. And then you say, okay, now we have wonderful results, but you use hundreds of GPUs to correct the number, and then maybe correct to an accuracy of 10 to the minus 3. But it's still, it's big words and big statements and LinkedIn and all.
Yeah, you are more, I guess, even describing error mitigation, right? So not the correction, but the mitigation.
The mitigation.
Yeah,
Yes.
that is wasteful in the sense of that there are lots of noise is generated and then averaged over, right? So and that doesn't seem to be able to generate anything that could compete with using these GPUs properly from the first time.
Yeah.
Right? So,
Exactly.
Qubit mean field, the symmetry breaking is due to the encoding, right? Or the German encoding.
No, it's not okay. It's not because so the easy way to avoid this would be that they generate the database that we use in it depends on it's fine because whether I have to be aware and how I change your operations, right? But you could do communication. And that's right. Where I need to do to set that
Yeah, but I can't do anything. I can't stop the recording. And that I don't understand.
And in order to say symmetry
and if I click on record, it says ask permission to record. Arthur, are you also recording? Because it looks like it's not me recording.
No, I usually record.
Okay, it says it's recording, but if I click on that, it's not allowing me to do anything.
On my screen, it says it's recorded.
Right, so that you are recording.
I wanted to pause it and I couldn't pause it.
Where's the this thing record if you press.
Yeah, but if I press on that, it says that ask permission. Okay, maybe it's because. Okay, what does this say? Yeah, yes, we know.
No, but I didn't press
Well, on Thursday, well, no, we don't have the Thursday. Thursday afterwards, you can basically just stay, you just sit in an office and
I feel like not actually.
So you are recording.
I don't think I am recording, but I have a control.
Okay, well.
So because you started the recording, right? And so I have pressed record.
I recorded a short thing, and
Yeah, and
then
then you
and then I restarted
Yes.
and asked to record again, and then it came out recording.
Yes.
But difference before the first trial is that now I'm on the cloud. I asked to save the cloud. And when I did that, I suddenly lost control of the file. So I don't know what's happening.
Okay, so what may happen is that it will record and it will send me email saying that it's on the cloud.
You basically just.
We'll see what happens, but I'm always recording on this one as well.
Yeah.
It's not as good, the quality, but
I do it sometimes.
Alright.
I guess for today, it's gonna work.
All right, cool. So there are these two challenges, and usually let's start maybe with moving towards addressing the first challenge. What are the possible ways to build unitaries? Because we talked about these unitaries already quite a bit, and I want to show eventually what do people have these days. So technically, this is like more the overview slide, and we'll go to some of the techniques specifically later. And so overall, because we have now mapping between qubits and fermions, you can, and the idea is that you don't go and build a like unitary that is exponentially large. You always want something that converges with relatively quickly. So that's the hope, right? And so you could use your intuition if you have one in the fermionic space, what exactly how to build these unitaries. And then once you have your unitaries, you could always go to the qubit space, because that's where you the quantum computer will understand what unitaries you want, right? So if you have generators for your fermionic space, and then you will go to the essentially you could translate these generators into the qubit. Here's the formula actually that I'm writing. So either you are in the fermionic space or qubit space, the formula for unitary always the same. It's a product of some exponential functions with the anti-Hermitian operators. And these operators could be written in the fermionic operators, say in a dagger, or in the qubit operators, right? And we know how to go between them. So it's just these two forms. If you feel more comfortable working in qubit space, you could try that, or if you have intuition in fermionic space, you could start with that. But it doesn't really matter. Eventually, the compiler makes this last step go into the sequence of gates. And in the early days, especially, let's say some of these papers by IBM 2017, 18, so they really, because it was not very kind of accurate device in the sense that you cannot put many transformations. You quickly run into the problem with generating noise and inaccuracies. So they try to squeeze out as much as possible by manipulating with the gates that their computers can do, right? So that's a hardware efficient approach that wasn't based on maybe fermionic or qubit-driven intuition, but just whatever gates your computer can do, you try to put them in different sequence and see if you could minimize energy. Again, using the same idea of variational quantum Eigensolver, that energy is the king, and it kind of allows you to know where you're coming closer to the ground state or not. But I generally don't recommend this approach, because it's very frequently run into the issues that you kind of have so-called barren plateaus, where manipulating with these gates doesn't really get you any closer to the lower energy. It just the space is big, and that just could make even energy higher in some cases, or will have no effect on energy. Now, in the case of fermions, what usually people work with is this fermionic algebra. So they start with Hartree-Fock state encoded as a product of the qubits, right? And then they apply, like in the normal electronic structure theory, excitations. Here, the notation is that ijk is for occupied orbitals, right? So usual picture of the when we did the Hartree-Fock, we have these occupied orbitals, very simply ijk orbitals, and ABC, and so on. unoccupied, and then you promote the excitations by doing creation of the unoccupied, doing on the unoccupied, and this other part, which does the opposite, it's there just because we need generators that are anti-permission, right? So that's kind of the difference between the quantum computing approach where we need unitaries and just a normal electronic structure where we don't care about whether our transformations are unitary or not, right? And then in the qubit algebra, we could do something similar in the sense that we could start with some product state, maybe the same Hartree-Fock state, maybe qubit mean field rotated state, and use as a generators products of Pauli's, right, as we talked, right? And then the question, of course, becomes how to choose this in an optimal way, because technically, in both cases, this and this, we have exponentially many choices to for this generator. So there's a big space of possibilities, and so there are very many methods developed already since 2014. That was the time when VQ was suggested. And there are just a few techniques written here. We have a review article on unitary couple cluster theory with a review of several methods from the list here. And generally, one can say that, which probably it's like more like intuitive picture here, is that in many situations, the fermionic methods allow you to conserve symmetries better, meaning that every step, every unitary, like if you have a total unitary written as a product of these unitaries that contain its individual exponents, right? I theta, I x, right? Something like no I here, right? In that notation. So individual unitaries, in case of fermionic algebra, it's easier to conserve the symmetries, and you could already see this here. Say number of A and A daggers is the same, and then number of electrons at least doesn't get broken. But there is you sort of paying the price for that usually, that your circuits in elementary steps become more and more deep, as they say, right? And that is not very good for the current architectures that essentially have issues that every time you do something to qubits, it's not exactly precise, and you start getting more and more errors essentially from these operations, right? And currently we don't have correction for this error, so the gate cost is something that you want to reduce. Now with qubit algebra, there the situation is somewhat opposite. It's qubit operators are closer to the ones that actually can be implemented as gates, and it's harder to maintain the symmetry because yesterday I realized I haven't finished some of this discussion. Let's say if you have a product like this that comes in the one electron from one electron excitation, from this type of terms, we have x1, x2. But now if we have a Slater determinant, which is like 1, 1, 0, 0, right? So 4 in total. So what the axes are doing, they are flipping essentially the qubits, right? And so this will be turned into like just a 0, 0, 0, 0 state, right? Because each ax will eventually flip the 1 to 0, and this is what you're going to get. And this is sort of a vacuum state. So clearly here we have 2 electrons, and here we have 0 electrons, right? So generally, qubit products, they don't conserve the number of electrons by themselves. You need the linear combination of them, and that's what fermionic these operators have. It's like just the linear combination of Pauli products. Okay. All right. So now these are the first results, as I was saying, 2017. Nature paper by IBM. And this is, I guess, here just to illustrate our first attempts in my group to understand how this things works, and also some of the symmetry breaking discussions that we already had. So what was done in this paper in the minimal basis, very small molecules, hydrogen, lithium H, and lithium H2. And what the dashed dotted curve is the exact calculation on the classical computer. Then the dots here are the results of the quantum simulations for the potential energy surface and everything. And then I guess this kind of shadow kind of some kind of plot. It's just actually simulation on a classical computer what quantum computer is supposed to give. And so what was surprising to anyone who knows quantum or chemistry in general is that there is a big sort of kink here in this area where things, if you follow the exact curve, they're supposed to be smooth, right? And the claim in the paper, you read it, and I'm surprised how this got published, but it was the first kind of experiment, I think, on chemistry, real molecules, and even in minimal basis. And the claim is that it's just not enough correlation. And when we looked at this, it was looking more like a symmetry breaking in the situation, that it almost looks like if you continue this plot, it should go somewhere here, and this comes from some other state.
Right? It's like the diabatic state.
Right, like diabatic states of kind of certain symmetry. And we decided, okay, it's probably happening because symmetry is changing along the coordinate that they follow, and we should use constraint theory, where it's not only about energy, but we rather put some penalty here that like operators like number of electrons or spin should be conserved. If they don't, if you are switching the number of electrons or spin, then you get a penalty for that, right? And so one should really constrain the energy here. And so that's what we did in the work that is cited there. So there are some technical aspects here that are almost no overhead. Majority of elements that we needed for this extra penalty is already in Hamiltonian. And we could also reduce the noise level. Technically, we do this constraint search because one can see that when things are measured, that the results of these measurements are consistent with the symmetries that one would like to have. And if they are not consistent, then it's just becoming because of the noise. Right? So technically, what we did here is a little bit of a shortcut, because the penalty is for the expectation value rather than for the variance, right? So if someone wants to generate a function that is an eigenfunction of the operator, you need to go for the variance of the variance needs to be close to zero, not the expectation value close to the right value, because you could get, say, 10 electron system by making a superposition of 9 and 11, 50-50, right? So, but in reality, that since this 9 and 11 electron systems could have really different energies, it doesn't really happen. And practically speaking, even this simpler constraint works quite well. So what we did, it's our first calculation on a quantum computer, not on IBM, but Rigetti. And the results that are actually obtained on the quantum computer, these dots with the error bars. And it's all in a very simple mean field level, but it was enough to see what the IBM people probably had in their calculations. And this is the hydrogen case. They had hydrogen, but they had also other systems. And in hydrogen, what happens if you do in the mean field level calculations? So this is a dashed curve. So usually in Hartley-Fock or in the Qubit mean field here as well, you converge to something that in the dissociation correspond to H plus and H minus, right? So half of the energy of those, and therefore this dissociation curve doesn't go to the exact value, but rather singlet goes to this weird limit, right? But if you want to kind of reproduce the Hartree-Fock, what you need to do is to do the constraint of the number and spin to be singlet. That's what the in-field theory then produces. And with the constraints, these dots, they follow this dashed curve, which is generated on a classical computer. And yeah, constrained VQE also will have null kinks. This blue curve is actually exact H2 ground state. And the triplet state here on the red, that is the state that actually generated the kink, because if you don't have a constraint and just use mean field theory, then you will have a ground state here, which corresponds to the singlet. And then after this point, it's going to be a triplet, right? So the reason is that indeed there is not enough correlation that they put, and we only consider mean field sort of solutions. Surprisingly, for the minimal basis in this system, the singlet requires correlation, but the triplet doesn't. And that's why at the mean field level, triplet is exact, but it's not exact. A singlet is not exact. And if you are doing mean field level, then you are, and you're only caring about energy, you will switch from the singlet to the triplet, because your variational quantum Eigensolver looking for the solution with lowest energy, right? But because the unitary is not allowing you to explore the entire space, it will look only within the single sort of slated determinant states. And then another interesting feature, the orange curve, that is H2 plus. And this is interesting because technically, if you don't put the constraints, then H2 plus you won't be able to obtain unless you somehow make sure that the number of electrons is a constraint to subspace of one electron, because H2 plus is always like excited state in this Fock space compared to the ground state, which is H2, like neutral, right? And of course, the mean field theory there is exact as well, because it's only one electron. Now, returning to the biggest kink they had in lithium H, we actually did this calculation on a classical computer just to see that indeed, if we don't do any constraints, that the mean field theory generates this kind of kinky structure that this is a mean field, this is the exact solution. And on the right dashed, we have a S square expression. So essentially, we're switching from the singlet to the triplet where S square eigenvalues 2, right? So that's happening in their lithium H calculations. All right. So just to summarize, VQE was suggested to address 2 problems of quantum phase estimation, which we'll discuss later: initial wave function and long circuits. And so then people start just using the VQE by itself. And it sort of introduced maybe 3 new problems: how to find the right state in the Qubit space, Fock space, and how to parameterize unitaries, also how to measure the Hamiltonian. That is something that we need to discuss further. Adding physical constraints generally helps, and this is not the only way in general to maintain the right symmetries. I guess I want to maybe point out, because it will appear later in various parts, but there are 3 general ways to introduce the symmetry. One is constraints, and 2 others. So one is constraint, you just modify constraints. This is just modification of your expectation value plus some lambda, then symmetry expression minus the value you want squared for one. And this is relatively cheap because all you need is just the expectation value of the symmetry operator. Then second one, which is relatively expensive method of this on the quantum and class could be expensive both on quantum and classical computer, and that is projection to the symmetry subspace. You can construct projectors, and instead of minimizing the expectation value of H, you just minimize the expectation value of the projected quantity. So the projection has an important property, P squared is P, right? So therefore you don't need two P's, one is enough. Also with commutes with Hamiltonian, therefore the thing that one needs to evaluate is really just this ratio, right? So now in this formulation with projection, you can violate the symmetry with the wave function, but the energy will be sort of energy of the projected state to the right symmetry. Okay, but the projections themselves, this is an expensive operator. Expensive in the sense that, let's say, if one wants to project to a certain number of electrons, so there are kind of at least two ways of doing that. Through Lagrange's formula, that's probably one of the simplest and straightforward way of writing this. So if you have in Lagrange's formula the operator minus some number of electrons, then yes, the right number, let's say, let's just say E minus E product of over I, which are not the right number. And then what you get is essentially if your number of electrons that you want to sort of project, it like the spectrum of this operator goes from 0 to like well, some reasonable number like 10 or 15 or let's say 100, right? So then it's a polynomial of 100 degree, because you need to project all the number of electrons that are not the ones that you're interested in. Okay, and so this operator is quite complicated in the sense of realizing it. If you want to put it on a quantum computer, then it needs to be a part of your Hamiltonian. Makes the Hamiltonian more difficult to deal with, and then you also need to consider the projector itself. So usually these formulations are not very easy to deal with. With the classical computer, of course, no one works in second quantization, just uses second quantization more like to do the bookkeeping, and then the functions that are used are already functions in the right subspace, right? So in that sense, we don't really usually use them as well.
So this is a projector kind of thing on the occupied space. So
in the Fock space, we have many sectors essentially, right? With number of electrons from 0 to number of orbitals,
yes.
In orbitals, right?
Yes.
So if you, let's say, construct a wave function that has maybe, as we talked in the break, if you're doing the mean field rotations, qubit mean field rotations, right? They potentially can break the symmetry number of electrons, right? So they could have a qubit split from the being occupied to being unoccupied, or to be somewhere in the state of partial occupation, right? So by doing these rotations, you could break the symmetry, but you may not even worry about it if you allow yourself to put a projector, right? So then you don't need to worry about your unitary being nice unitary that doesn't break symmetries. You could allow it to break symmetry, but the energy will be still from the part of the wave function that corresponds to the right number, right? So that's the approach which is using projectors. And projectors could be built for any symmetry operators. Standard techniques to do it. Lobdin projection is one of them, but there are others as well. And it's just this projection technique is not that simple algebraically. If you think about quantum computer, how to really implement this, because it becomes high degree polynomials in terms of operators. Right?
And this is the number operator?
Yeah, that's number
And
operator.
then the others are
No, those are the value of the number operator. It's okay. So how does this work? Imagine you have just a function with two possible number of electrons, 0 and 1, or 0 and 1, let's say. So then this projection, and you want to project to, let's say, 1, right? So then what you do is you have number of electrons minus, so you want to project the 0, and then here it will be 1 minus 0, and there will be only one, essentially there will be only one product. It's not very interesting. But let's say for making it interesting, we have 0, 1, and 2, right? So then this is going to be a part for projecting out the 0. And then there will be part that projects out 2, which will be an electron minus 2, and then an electron, which is 1, that we're interested in, minus 2. Right? So what this product does is when the function comes, let's say with see, if we come with 0 function, if we come with 1 function, and if we come with 2 function too. Maybe I actually made a mistake. Let's see. So for the 0 function, what the n electron will be here is essentially 0. And we will have for the 0 function, we'll have 0 minus 0, 1 minus 0. That is, we're going to 0 things, 0 minus 2, 1 minus 2. Right, so this will be an eigenvalue for the 0 function if it comes and meets this projector, right? And because 0 minus 0 is 0, so this and this, if these guys are non-zero, essentially, it's minus 2 divided by minus 1. And okay, so then this whole thing is going to be 0. So the coefficient in front of this function will be 0. If 1 comes, then it will be 1 minus 0 divided by 1 minus 0, which is 1. And then will be 1 minus 2 divided by 1 minus 2. So both numerator and denominator will be exactly the same. So this will give us coefficient 1. So this is exactly what we want. So that if we want to keep this component with 1 electron, it will be kept by this operator, right? And if the 2 comes, then in this case, we're going to get 2 minus 0 divided by 1 minus 0, and then 2 minus 2 divided by 1 minus 2, right? So then this part will 0 the whole expression, right? And so that's how Lorentzian projection works. You just need the operator. It's also related to Lagrange interpolation. You know, like in the calculus, they say if you know your function in a kind of few points, then you can create a polynomial which exactly going to be in those points. So this is what we're doing here. We're creating polynomial where the projection will be 1 in a particular point of the right value of the number of electrons and 0 in all other points. So that's what is built here. But for that, you need the nth degree polynomial for the operator if the spectrum has n eigenvalues. And that is becoming expensive if the number of eigenvalues is large. Okay, that's why.
The formula looks a bit weird. So you have NE operator minus NIE.
Right.
And
And
then
where
below you have N,
any which you are looking for,
okay,
right? So
okay,
yeah,
specific.
yeah. So like, let's say NES, and then I is not equal to S. Product over O, I not equal to S. Yes, that's a formula. So that then when the NE will be turned into this, it will be 1. And if it turns into the any other, it will be 0 in the right direction. All right, so yeah, projection is another way to do it, but it's expensive usually and very difficult to use. Now, the third way, which we will see some of the works, and the third way is the following: you construct unitaries. Third way, to preserve the symmetry, you construct unitaries that have generators that commute with symmetries. So specifically, if this is a symmetry, you make sure that the generators commute with symmetries. And then if you start with something that is also symmetric state, some state that is an eigenstate of the symmetry operator, then modifying that state with the unitaries where generators commute with the symmetry operators will not get you outside of the right space, okay? Because these generators will not change the essentially our state to be of their own symmetry. Well, you could easily see that S after S applied to U0, because S commutes with all the generators, it's the same as U as 0. Right, so this is the same as this, and then this is the same as S 0. So we've shown that the modified state is also an eigenstate of S. So this is the third way, and this is the most sort of efficient way. If you can, I guess it allows you. The only thing it requires is to put the circuit with the generators that don't break symmetries. But as I said, in the case of fermionic generators, this is what exactly happening with the number of electrons. The generators don't break it, but you're paying the price in terms of the gates you need to make sure that your generators don't break symmetries. Okay, yeah.
I have one question for the third way, like in the context of CI, for example.
Right.
This is basically also what's often done, where
Right.
the initial guess has some kind of symmetry, then you are supposed to get to the correct symmetry spin state.
Right.
But this often doesn't happen because of numerics, right? So in a lot of cases, you have to have some kind of shift or shift out the other spin states, like with the constraint in the first one. And does this also happen here? Is this also something that can happen? I guess maybe due to noise or something like that.
Could be due to noise, but usually if noise is large, then you have all sorts of problems, not only with symmetries. But I'm actually curious, what could you elaborate a little bit? I thought that in the classical computer, because we can use this symmetry adapted configuration state functions. This is
Yeah,
the
so it only happens in the CI. It only happens when you use permanent basis.
Right,
and in that case, those not eigenfunctions of
squared, right? But if you switch to CSFs,
then you don't have any problem.
yes, that's right.
But
So this is like switching to CSFs.
it is okay.
Yes, it is. Yes.
Okay.
And working with determinants is like working in the qubit space where you break some symmetries, right?
Okay.
But as like it's a very good analogy. Thank you. So with the determinants, eventually, if you have many determinants, when you diagonalize the Hamiltonian in a large subspace of determinants, you will recover symmetries because you're going after eigenstates of the operator that commutes with symmetries, right? So therefore, even though individual determinants are not symmetrically adapted, but the eigenstate that you obtain as a linear combination of those determinants will be symmetry adapted. So similar effects happen in the quantum computer is if you use at every step some transformation that breaks symmetry, but because you use many of them, eventually, and you're going after eigenstate of the operator, eventually you could recover symmetries. That's what we usually see some problems. But it's a bit of a debatable topic because there are some works there which start essentially saying that convergence may be suboptimal if you break symmetries. In some cases, people say, well, no, you actually benefit from breaking symmetries and then restoring it somehow. So it's a symmetry energy debate that I think very frequently happens. Some situations you benefit from breaking. In some cases, it's good to preserve. All right, yeah. So yes, that's all for this. And unitary couple cluster theory. That's something I want to present as one of the first techniques that people used for the VQE as a way to generate unitary transformations, borrowing the classical intuition, borrowing the intuition from the normal couple cluster theory, and it's a kind of somewhat funny story that some of you probably heard when we went to the conference. I already said quickly this thing that, as I understand, happened here is that the normal couple cluster theory is operating with the wave function, wave operator that involves the T, and the T is neither Hermitian nor anti-Hermitian. It just it is explained here. So it's just a sequence of excitations. T1 has all the single excitations. Small t's are amplitudes, and T2 is all double excitations, Tn and other excitations. That's how the normal couple cluster theory builds. So it's CC, let's say, as T. The typical level is a wave operator at the single and double level applied to the Hartree-Fock. And so, and then single and double level is just the exponent of T1 plus T3. Singles and doubles. Okay. All right, good. So then, so this been going on for almost like a century, like a couple cluster theory, maybe already a century, but the couple cluster theory was suggested in 20th century, in the beginning, and from condensed matter physics or nuclear physics. And so some people who are developing couple cluster theory, they been experimenting or suggesting essentially the alternatives. And one motivation to look for alternative is that this couple cluster theory is not actually variational, right? So the way we optimize the TM, the small parameters, is by just imposing orthogonality condition. So just to remind you quickly, if in order to create the couple cluster equations for amplitudes, what we do is we essentially write the first energy expression of this. So what happens is, presumably, if your T is exact T, then you will be able to say here generate the true eigenstate of H, and that will give you E of that state, ET check, and ground state energy. And then you get rid of T by this exponent, right? So minus T cancel this exponent, and then HF with HF gives you back 1. And so this is just E0. Right, so you kind of use the fact that you undo the transformation that helped you to get the eigenvalue, and then but this is just a single equation, and you have a lot of amplitudes to find in T. So what do? You use the other determinants which are orthogonal to Hartree-Fock one. right? So you can use the ones that have an excitation single to from the occupied to the virtual. And then in that case, if you do exactly the same thing, then you have a zero as a result, because what happens is that when this undoes this, this creates the constant, but Hartree-Fock and this determinants they are orthogonal to each other, so you have zero. But at least, even though you got zero, you get one more equation, and because it's all single excitations, you essentially get number of occupied times number of virtual equations. Right? You could put doubles and triples and so on. You get more and more and more equations to solve, and that allows you to get these amplitudes. But it's not variational. You're not minimizing energy. You're getting energy which is kind of solving these equations approximately. Now that has some issues, because in some problems where you dissociate, let's say, too many bonds at once, the couple cluster theory, well, it's very good in the equilibrium. But let's say nitrogen case, if we do CCSD, then in nitrogen case, this couple cluster theory dives down. If this is the exact curve, goes below, which is very non-variational, because we know variational principle is supposed to be giving you solution which is always on top of the exact, and so that's what we like about variation. All right, so how do we make things variational? Well, one way to do it is to turn this operator into something that is actually unitary. And the one way to do it is to create anti-Hermitian operator. If you have any operator, to make an anti-Hermitian is you subtract the adjoint, right? So adjoint operator. So this will be Hermitian no matter what T is. Great. So that's what Rod Bartlett, one of these big developers of couple cluster theory, Bartlett. So he suggested that in one of his papers, and even at that time, I guess there were some comments that, okay, this will give us some unitary transformation that you can try to optimize. It's not gonna lead to the equations that we need to solve, but you need to optimize, and it's difficult to optimize such unitary on a classical computer, but maybe on a quantum computer we can do it. So that's the kind of beginning of that story. Okay, so Rod Bartlett and his group, they don't work on a quantum computer, right? So they and it's from the private conversation with him, I had no idea what quantum computer can do, right? So they just suggested it because it's unitary, rightly so, but whether that can be done on a quantum computer or not, they actually didn't think about that too much, right? And in reality, we know that this is just very complicated operator that we are trying to build here, because if you look at this unitary, it contains a lot of terms potentially, and these terms turns out they don't commute, right? And a quantum computer, as I said, it requires you to have an exponential function of at least the Pauli product, right? And each of these terms, they create polynomial number of Pauli products in a single exponential function, and they don't commute, right? So we don't know how to deal with that. So, well, sort of in the exact way. There are approximate ways, and that's what people start using. So the next, I guess, step in this story is that when Rod Bartlett put it in the paper, people who are actually working on a quantum computer, they try to use this as a first way of introducing some unitary ansatz chemically motivated in quantum computing, right? And they needed to deal with this giant exponential function, and they decided, okay, so here are some comments on the fact that the TNs themselves are good, but and they do commute. So you sort of you can every term here and every term here, they all do commute. But once you put T dagger, things become non-commutative, and that complicates things. And we cannot just implement this thing, right? So what people start doing is a so-called Trotterization, right? So Trotterization is a relatively simple idea that tries to address non-commutativity. So with numbers, this is the same as this. And if A and B are numbers, then we have this. But if they're not numbers, if they're operators, then this is not true anymore. But you could still essentially do this, but approximately. And it turns out that in reality, you could say that this is approximately by adding some parameter here. It could be written like this. And then there's an exponential function of the commutator with the t squared divided by 2. And then there's an exponential factor of the commutator, like nested commutator A, B, and there are more, 3 divided by 6 or something. So there are more factors like this. Now, why is this useful? Because if you could make the t small enough, then you could suppress these factors, right? So the idea then is, okay, well, let's, there's even Trotter theorem that says that if you do t divided by n into the nth power and do limit n to infinity, then we could write this as exponent of a, t divided by n, exponent of b, t divided by n. This is nth power. Okay. So by making n large enough, your t is very small. So you suppress all these extra steps or extra terms, provided that the commutators kind of behave nicely, that norm of commutators doesn't blow up. So because if these are operators, if their eigenvalues become too large, well, then the norm becomes large, and that may undo the things we do with the suppression of this t factor, right? So, but those are mathematical subtleties. In general, you could always do this, and that's what people start doing for the UCC, because you could chop now this, let's say, in any theory, you don't go to all the excitations. That's see a very reasonable approach where we go to up to the second level of excitations of the second degree, right? Double excitations. Then you need to partition, and that's what like the partitioning is done in this way, where let me introduce this kappa, the singles and doubles, all they are like these are ij excited to AB, but we excite them in the anti-Hermitian way so that they can be generators. Then using the Trotter, we could write the exponential of the sum as a product of exponential functions, right? And there is a large K, I guess a little bit maybe confusing notation, kappa and K, but K is this factor that you want to make large to make this approximation accurate. So that single double unitary is approximately equal to this with a finite kappa. All right, so that's what is usually done, and usually people also very aggressively, especially with quantum computers these days, they try to use k equals 1. So essentially very drastic approximation. And also this formula is order dependent, depending on how, since these guys don't commute, depending on how you put what sequence you put these products, you get like different unitaries essentially. And this one is also order dependent. Sorry, I said order independent here because we will, I guess, discuss this more in a few slides. but it turns out that these generators, the single ones, they kind of form the Lie algebra, and for the Lie algebra, the order actually doesn't matter. We'll get to that in a moment, but or maybe at the next lecture. But for the doubles, it's order dependent, and depending on how you put doubles, you get the different unitaries. Okay, yeah.
Yeah, so on classical computers, sometimes, or something else is used, which is called the Bernoulli expansion. And usually, I think the benefit of it is that when you would try to expand this similarity check for Hamiltonian for UCC, then you have like set perturbation orders. You can basically separate the operator into, and yeah, you basically know that conversion from perturbation. So you know why factorization is like preferred in the world?
Well, I'm not familiar with the Bernoulli. Does it also treat the exponential function, exponent of the sum into the product of exponential? Or it's something else? Because
I mean, I know,
there's
to be honest, I'm not sure, but I know that it is used for UCC on classical. So I assume it has to. But I'm not sure whether it's, I guess maybe if it's not product of exponentials, then you cannot, it's not useful in the computing sense. You cannot separate this.
right. So general idea of the where we're going in the quantum computing world is if you have a complicated operator presented as a product of simpler ones, right? So if it's not factorizable in that way, then it's not clear how to do it. That's why Trotter is very natural way of dealing with the complicated exponential operator. All right, but just let me get to the, I guess, punchline here is that this trotterized sort of form, which is approximate in the derivation I just showed, can be actually you could get to the unitarized version of couple-cluster theory differently and without doing any approximations. Okay, and so the idea would be that to remember that if you start with a normal couple-cluster theory, there all the like we only have excitations in exponential functions, and they all commute. So exponential of the sum of excitations is the same as a product of exponential functions of excitations. So let's just write that as a product, and there's no approximation here. And then for every essentially exponent, we add Qubit conjugated part for the generator to make it unitary, right? So we go from this excitation to kappas, which contains excitation minus the excitation, right? And that is the process of making it unitary. It will make things order dependent. There is no kind of way avoiding that, but there is no need to do any Trotter approximation for that. It's just a different way of obtaining unitary, right? So from the couple cluster theory. So this is somehow was missed initially because I think because of that sort of interesting maybe broken conversation between the two communities, and one community offered the unitary form to another, and another one started trying to use it for quantum computers, and then they required Trotter, but here we don't need Trotter, and the order problem becomes more severe than K more than one case. Okay, so what this is referring to is that if we do Trotter and we actually use the large N, then the order dependence it could be suppressed because we're starting with an expression that has no order dependence, right? But in this case, there is order dependence, and one may ask, okay, now how big is the order dependence? How good is this construction? Depending on how, like, in what order you put the double excitations. And people from Virginia Tech, actually, this is a paper, and I'll post it in the reading materials. They looked at the various orders and found that well, the dependence is quite significant. So these are on the upper row is like potential energy surfaces. Even on those surfaces, you could see the color scheme is a little bit strange here, but maybe not the most contrasted. But yeah, fully shuffled, I guess, is the part, the orange part, which greenish part that sort of have shown you how different the energies are. And the lower row is the errors. So there it's clear that order actually matters quite a bit. So here I have just a summary in kcal per mole for the systems they looked. Yeah, it's definitely more than chemical accuracy essentially by just shuffling the double excitation, the excitations, you could get nitrogen 30 kcal per mole difference. And then natural question would be which ones to choose or how to choose the optimal order. For this case, yeah, that could be yeah, question to one can try to address. But it turns out that yeah, I will discuss this. Yeah, it could be there could be even worse consequences of that. It just not only that we don't know, maybe there we are using that suboptimal order, but there are other issues with this kind of UCCSD technique where we have a factorized expression. But at this point, I guess I'll stop now, and we'll discuss it later, and also how the community kind of address this issue as well as an adaptive scheme. That's the way to so resolve this problem. Okay. Okay. See you next tomorrow.
Yeah. So let's see now if we can actually save now this recording. What?
I will just end the meeting for.